The binomial distribution is a very important and very useful way of understanding all sorts of things in the real world. So, when does this apply? First, it applies when we're going to have a series of events happen that we're going to call trials. So we're going to have a series of n trials. Every single one of those has a result that's going to fit into one of two categories, a success or a failure, a yes or a no, that sort of thing. Every single trial must be independent of all the other trials, so one doesn't influence the other one, and the probability of success of each trial remains a constant. There's some p, there's some number which tells us the probability that each trial will be a constant. So, for example, I could flip a coin 15 times and say, what are the probability that I'll get exactly 10 heads out of 15 flips? If I roll a die 5 times, I could say, well, what's the probability that I'm going to roll exactly 3 4s, that the number 4 will come up exactly 3 times? If a family has 5 children, I can say, what's the probability that they'll have 2 girls and 3 boys? We can calculate all of these probabilities given the number of trials, n, and the probability of success of each trial, p. Let's work this out in detail. Let's take that dice rolling example. So there's the scenario. I'm going to roll a die 5 times, and I want to know what's the probability of getting exactly 3 4s out of the 5 rolls. So I'm going to get 3 4s, and then 2 other rolls will be not a 4. This means I would roll not a 4 2 times. So, well, what are these probabilities? The probability of each success, each 4, is 1 out of 6. It's an ordinary 6-sided die. Probability of each not 4 is everything else, 5/6. Since each roll doesn't influence any other roll, they're all independent of each other, we can multiply these guys together. I got 3 4s, so I have 3 1/6, and I multiply them, and I've got 2 not 4s, so then I multiply them by 2 5/6. So 1/6 times 1/6 times 1/6 times 5/6 times 5/6, or 1/6 to the power of 3 times 5/6 to the power of 2. Multiply all that out, and I get 0.0032. That's pretty unlikely. That's less than 1%. But that's not the answer, because we're not done here. There's more than one outcome to consider for this event. There's more than one way this can happen. These 4s could come in any order, and they all could happen. We got to count them up separately. You could get the 4s first, and then 2 other things, or the 4s could come last. We need to figure out how many different ways you can arrange 3 4s and 2 not a 4s out of 5 times. So how many ways can we do that? Turns out there are 10 different ways to arrange 3 4s and 2 not 4s. So you can see we listed them out here. At the very first, we list, okay, suppose you get your first 3 rolls are the 4s, and then the fourth and the fifth rolls are not 4s. Okay, that works. Or you could roll a 4, a not 4, a 4, and a not 4. Or you could roll a 4, a not 4, a not 4, and then end by rolling a 4. And then there's all these different ways of doing this. I went through here and I added them all up. So these are all 10 ways of ordering 4s and not 4s. Each one of these outcomes, every single one of these 10, has that same probability of 0.0032, because it doesn't matter which order we multiply our 1/6 and our 5/6. So I can take that probability, 0.0032, multiply it by 10, and I get a probability of 0.032. There's a 3.2% chance of rolling 3 4s and 2 something else's if I roll a die 5 times. That's still not very likely, but that's more likely. That's interesting. Okay, so how do we do this in general? In this case, I sat down, I took 10 minutes, and I figured out the 10 ways of doing it. What if I want to do this in general? Or what if somebody wants to roll the die 10 times or 20 times or 100 times? How do I figure out all the different ways of ordering all these sorts of things? I can do this with the amazingly powerful mathematical function of a factorial. To write a factorial, we use an exclamation point. So 5 factorial, with a factorial, you take a number and then you multiply it by all the whole numbers smaller than it, all the way down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. Let's see, 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120, 120 times 1 is 120, so 5 factorial is 120. Factorials are ways that is a function that allows us to count up all the ways of ordering things. If I'm using R, I just type the command factorial of 5, and it will calculate that 120 for me. Now, the reason, so we take the 5 factorial, so that's the way that we can arrange our 5 things. But then, well, the 3 4s, it doesn't matter. It's not like the 3 4s are distinguishable from each other. This 4 and that 4 mean the same thing. So I take the 5 factorial, I divide it by 3 factorial, because the 3 4s can come in any order. I don't care which 4 comes first. And then the 2 not 4s, again, can come in any order. So then I divide by 2 factorial. So I have 5 factorial divided by 3 factorial, 2 factorial, or 120 divided by 6 times 2, 120 divided by 12 is 10. There are 10 different ways of arranging 3 objects and 2 other objects into a line of 5 total objects. In general, the number of ways we can order k successes from n trials, so k is the number of successes I've got, n is the total number of trials I've got, is n factorial over k factorial, and then n minus k gives me the number of, in this case, failures, not 4s, n minus k factorial, and that allows me to calculate all of this out in general, no matter how many things I've got, no matter how many trials, how big k and n are, that formula is bulletproof. It will always work. It will always count the number of ways that things can be ordered. So I can put that all together and get the binomial formula, a general formula, which will allow me to calculate the probability of absolutely any binomial event. In this case, I wanted the probability of 3 4s out of 5 rolls. So there's the 5 factorial over 3 factorial. 2 factorial tells me the 10 ways that this can happen, the 10 orders for these things. I then multiply that by the probabilities, 1/6 to the third, 5/6 to the second power, multiply all that out, and I get 0.032. And so we can generalize this. If I have a much bigger problem, I can't calculate all the individual pieces and figure out the orders, I can apply the binomial formula. The probability of getting k successes out of a total of n trials is n factorial over k factorial, n minus k factorial. I then multiply it by p to the k. P is the probability that each individual trial is a success. So if I've got k successes, then that probability to the power of k. And then, well, let's see, the probability of failure is going to be 1 minus p. And then how many failures have I got? Well, that's just n minus k. So the probability of failure to the power of the number of failures I've got. Put all that into a big calculator and it will spit out the precise exact answer. So, for example, suppose I want to flip a coin 15 times. What is the probability that I will get exactly 10 heads and 5 tails out of 15 flips? Well, in this case, n is 15. I got 15 trials. K is 10, that's the number of heads. Probability of heads, the probability of success each time is 0.5, so I put that all into the formula. I have 15 factorial over 10 factorial, 5 factorial, and then I've got 0.5 to the 10th, the probability of all those 10 heads, 0.5 to the 5th, the probability of those 5 tails, multiply all that out, and I get 0.092. 9.2% chance that if you flip a coin 15 times, you will get 10 of those flips will be heads. R can do all of that. The wonderful, magical, amazing command that exists within R is dbinom. And so then with that, I just put in 10, 15, so I put in k first, the number of successes, there's 10, 15, then it was my n, probability of each success is 0.5. I stick that into R, and immediately it spits out the number 0.092. Let's do another example. Suppose there's a multiple choice quiz in some class. This quiz has 12 questions, 4 answers each, A, B, C, or D. Supposing somebody hasn't studied at all and is just totally randomly guessing their answers. What's the probability that this person will get 7 questions right out of 12? Well, what are our parameters there? Let's see. We have n equals 12. There are 12 questions. K equals 7. We want to know the probability of getting 7 right. P equals 0.25. The probability of getting each one right is 25%, 1 out of 4. We put those numbers into the binomial formula. We have 12 factorial over 7 factorial, 5 factorial times 0.25 to the 7, probability of getting those 7 right, times 0.75 to the 5th, the probability of getting those 5 questions wrong. We multiply all that out, and we get 0.011 or 1.1%. So the lesson is, kids, don't do this at home. That's not the way to try to pass a class. We can also feed these into R's dbinom command. 7 successes out of 12 trials with a probability of success of 0.25, and R will give us 0.011. let's mix this up a little bit. What if the question is not of the probability of getting exactly 7 questions right? What if I want to say, well, what's the probability that someone gets 7 or fewer questions right? What if I want to know that? 7 or worse? Well, okay, so n is 12. We have 12 questions on the quiz. P is 0.25. The probability of getting each question right is 0.25. But K, well, I want K to be 7 or 6 or 5 or 4 or 3 or 2 or 1 or 0. So I need to stick each and every one of those K's into the formula and add up all the results. So what do? Well, okay, I got 12 factorial over 7 factorial 5 factorial times 0.25 to the 7th times 0.75 to the 5th. That gives me the probability of getting exactly 7 questions right. And then I have to add 12 factorial over 6 factorial 6 factorial, 0.25 to the 6th, 0.75 to the 6th. That's the probability of getting exactly 6 questions right. To that, I add 12 factorial over 5 factorial 7 factorial, 0.25 to the 5th times 0.75 to the 7th. That's the probability of getting 5 questions right. And I got to keep going. I got to add that thing up for 4 and for 3 and for 2 and for 1 and for 0. There's a certain chance you'll get none of the questions right. If I add all of that up, I get 0.9972. That means that's very likely that you'll get 7 or fewer questions right. You're most likely to get somewhere around, well, I don't know, 3 questions right or so, because 3 is 1/4 of 12. So we add up all this, we get 0.9972. Wow, what a long, tedious, intricate, complicated procedure. If only there was some better way to do this. Oh my goodness, look at this. R has a command for this. Check it out. In R, the command is P binom. Remember, the previous one was D binom, the binomial distribution. Here, P binom gives us the probability of getting this number of successes or fewer. This just automatically adds them up. All in one command, all in one go. P binom of 7, 12, 0.25 will calculate that 0.9972 probability all in one go. Let's do another example. Okay, suppose, same scenario, the multiple choice quiz, 12 questions, but suppose I want to know the probability of getting 7 or more questions right. Oh my goodness, 7 or more questions right. Well now, again, n is 12, p is 0.25, k is now 7 or 8 or 9 or 10 or 11 or 12. So okay, I go through the formula. I can put in 7 and then 8 and then 9 and then 10, and then I would have to put in 11 and 12. Add those all up. If I do that, I'm going to get 0.014. How do we do that in R? Let's do that the easy way. Well, in R, remember, P binom gives us the probability of getting this outcome or less, this number or fewer successes. Well, I want the probability of getting more successes, but probabilities have to add up to 100%. So I can do this with subtraction. I do 1 minus P binom of, notice, 6, 12.25, all right? I want the probability of 7 or better, so what do I got to subtract off? I got to subtract off. I got to take 100%, 1, and subtract off the probability of getting 6 successes, or 5 successes, or 4 successes, or 3 successes, or 2 successes, or 1 success, or 0 successes. And that's what P binom gives me. So I do 1 minus P binom of 6, 12.25, and that will allow me to calculate that this is not very likely. The chances of somebody, maybe the minimum passing score on the quiz is 7 or better out of 12, not very likely, only a 1.4% chance of that happening. All right, to summarize, the binomial distribution applies whenever we have a series of n independent trials where the results of each fit into one of 2 categories: yes or no, true or false, success or failure. Every single one of the trials gives me 1 bit of data. In this, we use n to represent the number of trials, k to represent the number of successes we want, and p is the probability that each trial will succeed. And therefore, the magical, wonderful, powerful formula that allows us to calculate all of this is probability of getting k successes out of n trials with a p probability of success is n factorial over k factorial times n minus k factorial times p to the power of k times 1 minus p to the power of n minus k. In R, we can do this straightforwardly with the D binom function, which gives us the probability of having exactly k successes out of n trials with a p probability of success. Or if I want the probability of k or fewer successes, I want to add up all of those, I use P binom of k, n, p.